Okay, so the next section in chapter 6 is getting into actually a pretty important concept that does pop up a lot on the AP exam, and that's Newton's law of gravitation, or Newton's law of gravity. So before, we've talked about the gravitational force as being the weight, and that's just simply mass times gravity. Well, we're going to talk into a little bit more this unit, or this section, about where this G comes from, and also how your weight can change on other worlds, getting into Newton's law of gravity and where that concept comes from. So gravity itself obeys what's known as an inverse square law. So there are two things. So anytime that I have two objects that are near each other, they experience a gravitational force. And this might seem kind of weird, but it means that any two objects, if they are near each other, they will attract each other. So there's always an attractive force between those two objects. The force of mass 2 pulls on mass 1, and mass 1 pulls on mass 2. Similar, when you're on the Earth pulls on you, and you pull back on the Earth. So there is an action-reaction pair. But the things that matter, first off, the force is inversely proportional to the square of the distance between the two objects. So if I look at my formula here, this r squared value is on the bottom. That's saying that the further away I get from something, the less I feel its impact. And the perfect analogy of this is thinking about like magnets. So when I have two magnets really close to each other, they're either very attractive or very repulsive. But when I get pretty far away from each other, there's a very little effect that they have. Similarly, two objects that are very far apart from each other don't pull on each other as much as two objects that are very close. The other thing is that the force is directly proportional to the product of the masses. So right here I have M1 and M2 multiplied by each other. And the heavier the mass is, the more they pull on each other. So when you think about it, to kind of sum this all up, the Earth and the Sun exert gravitational forces on each other. So the Earth pulls on the Sun pulls back on the Earth, and that's what helps us orbit the Sun. And we'll talk more about that a little bit later. But at the same time, the Sun doesn't pull me off the Earth because of how close I am compared to the Sun. So that r squared factor is a thing, as well as the masses. And also when I jump up, I don't feel the Earth going up as much because of its masses. So let's take a little bit further or a deeper look into this. And we'll do that with an example problem. It says you're seated in your physics class next to another student that's 0.6 meters away. Estimate the magnitude of the gravitational force. Assume that you each have a mass of 65 kilograms. So the gravitational force, that's the attractive force, always attractive between two objects. Later on in the year, we'll talk about Coulomb's law. And Coulomb's law is a little bit different. That has to do with electric forces, and it's a very, 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 very similar formula, but it's just a little different because we're dealing with charges, and charges can be attractive or repulsive. But for us, this is just attractive. So it's G, which is Newton's gravitational constant, is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of the first student, which is 65 kilograms, times the mass of the second student, which is also 65 kilograms. That's right around 130, 140, 150 pounds, divided by this 0.60 meters, and of course that quantity is squared. So that's all we're saying. We're saying that when I have two masses next to each other, there is a force that's bringing those two together. And if I quantify that force out, I get about 7.8 times 10 to the negative 7th newtons. And when I think about that, that is 0.1234567 newtons. Wow, that was funny that it had 6, 7, 8. Anyway, the force is essentially immeasurable. It's too small to actually cause an effect, because then if I look at, acceleration equals force divided by the mass, if I look at this really, really small force divided by your mass of 65 kilograms, that's going to be even 100 times smaller. So it's just, it doesn't cause enough based on our masses. But when we get into the masses of planets, it absolutely causes more than enough. This is a stupid video. I just love it. Can a person have their own orbit? Kind of is the answer to this question. This is a Family Guy video of when Brian, who's, in case you don't know, Brian's the dog. Oop, I don't know why that. Okay, Brian's the dog. He starts throwing objects to Peter, and they start orbiting him. And the reality, of course, would be that doesn't happen. And the reason that doesn't happen is because we are not, as people, we're not the sufficient mass in our system. The Earth is. So that's why the TV would fall down, the apple would fall down, but it's just a stupid, funny little thing. But if I were in the middle of space, in the middle of nowhere, I could potentially have the dominant mass around, and maybe then I could have my own orbit. All right, so I got a quick check. The force of planet Y on X. So planet X is 2m, planet Y is m. There's some distance apart, and there's this force of X on Y, and my question is, what about the force of Y on X and X on Y and how they relate to each other? They are going to be the same. And the reason they are the same is this is Newton's third law. Planet Y pulls on planet X pulls on planet Y. This is an action-reaction pair. This is Newton's third law, so they experience the same force. Another quick check. Here I have gravitational force is 1,000,000 newtons. What will the force be if I double the distance? Well, if I look back at my formula, it's g m1 m2 over r squared. So if I double this distance r, it's going to be 2 squared, so it's going to end up being a quarter of the force, and that'll be 250,000 newtons compared to the original 1,000,000 newtons. So on other planets, I can use this concept of gravity and Newton's law for gravity. So the weight on the moon, for example, I could calculate that, how much you would weigh on the moon. On Earth, the weight is mass times gravity of Earth. On the moon, it's mass times gravity on the moon. Well, if I set this force of the moon equal to mg, right, then actually these two, this little m right here, that's the mass of me, this is the mass of me. Those cancel, and then I get this formula that the gravity on any planet ever, anywhere, is based on still that Newton's gravitational constant, the mass of the planet, and the radius of the planet squared. So this is actually how astronomers and astrophysicists use data that they have to calculate free fall acceleration on other worlds. They can figure it out just by using this actually really simple equation, and then they can make accurate predictions about, for example, if you're gonna do a flyby with a satellite, and that's a huge concept. If you look into the history of astronomy, there are countries that have launched satellites into towards Mars and stuff. And they'll miss Mars because they don't properly account for, first off, the trajectory of the satellite, which is really hard. If you're thinking about launching a satellite to Mars, you're talking about where it's you're aiming at a target and where it's going to be in 9+ months. It's a really difficult thing to do. You're not aiming at a bullseye. You're aiming at where a bullseye is going to be millions of miles away in thousands of days. Okay, so it's really tough. But also, if you don't correctly account for the free fall acceleration, the gravitational pull of the planet won't be strong enough if you're not close enough, or it'll be too strong because you're too close, and it'll either not pull the satellite in, or it will pull the satellite directly into the planet. And then in either case, you can't launch a satellite into orbit around that planet. So really interesting things or issues that we have to tackle if, in fact, we do ever want to colonize Mars. So here's a quick little conceptual example, not that I got off track at all in the last 2.5 minutes. Calculating g on Earth, if I plug in Newton's gravitational constant and the mass of Earth and then the radius of Earth, I get a free fall of Earth of 9.518 meters per second squared. And you're saying, wait a second, free fall acceleration on Earth is 9.81, or depending on your belief system, 9.80 meters per second squared. Why is this 9.518? Well, I would say that it's close enough. And the reason is, of course, we have the mass of Earth to the nearest, well, I mean, if it's Oh, you're going to hate this one. 5.972 times 10 to the 24th kilograms. That's I'm sorry, I'm going to get rid of that point. 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 kilograms. Okay? You see how this is a problem? If this is off, if this whole line of zeros is approximated, that's a really long line of zeros. And of course, the same thing with the radius, that's going to lead to some type of round off error. But 9.81 or 9.8 compared to 9.5, yeah, that's close enough. All right, another quick check. 60 kilogram person stands on each of the following planets. On which is the weight the greatest? Well, your weight is, of course, mass times gravity. And that's your mass times gm over r squared. So if I were to evaluate 2r, 2m, 3m, 3r, so this is m over r, so my g is going to be 1 over 1 squared, which is, we'll call that 1. In the second one, I got 2 over 2 squared, so that'd be 2 over 4, which is a half. And in the third one, I got 3 over 3 squared, which is 3 over 9, which is a third. So I'm going to weigh the most, actually, on this planet. Now, you might say, wait a second, that doesn't make sense, because Jupiter, I would feel really, really heavy. And in fact, Jupiter does have a free fall acceleration of, I believe, around 27 meters per second squared. And the reason it is because this mass right here, it's dense. Jupiter is a dense planet. Physicists believe that if Jupiter was just a little bit more massive, it would have become a sun and not a planet when all the mass came together. So you're talking a significantly different amount of mass, and that's why it has such a higher free fall, and that's why we would feel really heavy on Jupiter. Anyway, that's your quick little introduction into free fall acceleration and where it comes from. The next thing that we're going to take a look at is an application of free fall acceleration, and we'll talk about gravity and orbits and how they impact one another, and we'll do that in the next segment.